Karnaugh map, or in short, this is called K-map. It's the tools for you to minimize Boolean expressions, or in other words, you can minimize logic circuits using K-map. And we're going to spend most of the time today looking at K-map, how we can construct one and how we can minimize logics using K-map. And then the central theme of what we discuss is mostly on sum of products, or in short, we call SOP. So we're going to minimize logics related to sum of products. So these are the subtopics or the relevant topics that we're going to look at in this lecture. The learning outcome related to this topic is on analyze combinational digital logic circuits. And what you're going to, or what I expect you to get out from this is to be able to construct K-map, minimize digital logics using K-map, and then implement digital circuits from Boolean expression. So you from your minimize logics or Boolean expressions, you're expected to know how to implement the Boolean expression into logic circuits. And then the last bit is to be able to differentiate the different form of Boolean expressions and also understand the terminologies used in terms of Boolean expressions. So that are the learning outcome that you are expected from this topic. Okay, so Karnaugh map, or in short, I will use K-map a lot. So in this example or in this discussion, it consists of a two-dimensional, or most of the K-map that we're going to use in this module are restricted to two-dimensional. Although I put in bracket there, it can be extended to three-dimensional, depending on the number of variables in your function or your Boolean expressions. So the best way to discuss this K-map is first to look at an example. So if we have a Boolean functions given here, which is x bar n with y, and then O with x and with y bar, and then O with x and y. Okay, so in these expressions, so we have two variables. The variables is x and y. And because it's two variable, so there are four terms or possible terms can be used in these expressions. Okay, so 4 is 2 to the 2. 2 is the number of variables, so basically it's 2 to the n, and n is the number of variable. So in this case here, we have n equals to 2, so there are 4 possible terms in our expressions. But the expressions given just now, there are 3 terms there. So which means that if we have another terms, 4 terms that will include all possibility of this function, which means that it will be equals to 1. So all 4 possibility in it. So for 2 variables, so you can fill up a 2 by 2 grid. So 2 by 2 is 4. Okay, so a grid like this, a 2 by 2 grid is what we call the K-map. And then we can list down the variable as the axis of this grid. So we use one side as X and the other side is Y. So one way of doing it is to list down exactly all the possibility as the axis of the grid. Another way that you find is you can make one side as the X variable, the other side is Y, and we use 0, 1, and 0, 1. There's another way of listing your K-map. And the entry of each of these grids. Okay, so the cell here. So for example, I put down here cell A is called the Minterms because we're discussing about sum of products. So this refers to Minterms of sum of products. Okay, so, or in short, we call it S or P. So where is it sum of products? Okay, so these are all our products term. And then we sum all the product terms. So this expressions here is called sum of products. And each of these terms here is called Minterms. Okay, so our cell A is the Minterm for X bar, Y bar. Okay, so it's just like your X and Y coordinate system. So this is for X bar, Y bar. Okay, so our B cell is referred to X bar, Y. Okay, so this terms here is X bar, Y bar. This terms here is X bar, Y. I'm sure you can guess or deduce all the terms or Minterms of all the other cells. So for example, here will be X, Y bar. Okay, so X here, Y bar from here. Okay, so Y bar, X, and then this will be X, Y. So this Minterms here is X, Y. Okay, so that is how from the variable links to each of the cell on this 2 by 2 K-map. So in this example, the function that was given just now, so we have for every Minterms in the functions, I'm going to put a 1 in the K-map. Okay, so our functions here that's given X bar Y, which is 1 Minterms. So in terms of our binary, so this is 0, 1, this 1, 0, and 1, 1. So in terms of binary, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3. Okay, so we can sort of map our K-map using a binary number. Or if we draw this as a truth table, so we can list down all the possibility of our X and a Y. So we have 0, 0, 0, 1, 1, 0, 1, 1. So for our functions, so 0, 0, which means it's X bar and Y bar. We don't have a minterms here, so our truth table here is 0. So 0, 1, which is our X bar and Y, we have a minterms in the function, so will be equals to 1. And then 1, 0, which is X and with Y bar, this is 1. And then X, Y, which is 1, 1, both X and Y is true. And then we have a 1. So in terms of our X and Y variable, in terms of the decimal equivalent, zero, 0 gives us 1, 0, 1 is 1, 1, 0 is 2, and then 1, 1 is 3. So we sort of can put an index in our K-map cell. So for 0, 0, which is this location 0, 0, 1 is this location, and then 1, 0 is this location, and then 1, 1 is this location. So all we do is we put in, so for the 0 location, we have a 0, so we put a 0 here. For the location of 1, we have a 1, so we put a 1 here. And then for the location of 2, there's a 1, we put a 1. And then location 3, there's a 1, we put a 1. Okay, so this is how we translate from the functions into the K-map, or from the truth table to the K-map. So what the 0 actually means is that it's the absence of a minterms in our Boolean function. So in this case here, our functions, the minterms that absent is X bar, Y bar. So this minterms is not present in our function, and therefore we put a 0 in the K-map. Another way of expressing these functions using a mathematics term, sort of a sum. So it's a sum of products. So each of this is the minterms of our products. So this refers to 1, referring to the minterms of X bar Y, or in terms of our binary, it will be 0, 1. And then 2 is the minterms of X, Y bar, which is binary equivalence of 1, 0. And then 3 is X and Y, which is a binary equivalence of 1, 1. And then we put a 3 there. So it's the sum of the minterms of 1, minterms of 2, and then minterms of 3. Okay, so this is the minterms locations of our products. And then the sum is the summing up all the minterms. So this is another way of expressing the same Boolean expressions in terms of sum of products. expressions. Here I put down red here, which is the number I put down here is as the binary equivalence of the minterms, or in other words, is the index locations of the cell of the K-maps. So here's a simple example. Okay, so we have a functions x bar y, or with x y bar. So maybe you can head to, or you can try this out, see whether you can put that expressions into K-map. Okay, so the first thing we want to do so we're going to put these expressions, each of these minterms onto K-map. So we have the first one is x bar and y. So x bar and y. So this is this location here. For the one. And then we have x, and then y bar. Okay, x, y bar. So this location here, so we put a 1 here. So the other two minterms is missing from these expressions, so we're going to put a 0. So in our sum of products or SOP format, so this is the sum of the minterms of 1, 2. Okay, so that is how you can put from the expressions, Boolean expressions, into K-map, and then how you can write it down in terms of the sum of products format. Okay, so this is the first step. You have to be able to convert or translate from the expressions into K-map. So you have to have all the minterms in order to translate into the K-map. So next we want to look at how we can minimize Boolean functions using K-map. Okay, so the whole objective of using K-maps is to minimize the functions. So once we have drawn out the K-map, the procedure to minimize the functions is as follows. So we have to identify all pairs of adjacent one on the K-map. Okay, adjacent meaning that is next to each other, horizontally and vertically. So in this example, so this 2, 1 is not adjacent to each other. Okay, so they are not horizontal or vertical. So once we identified pairs of adjacent ones in the K-map, we can draw loops around each pair. So I'm referring to pair here because we are still dealing with 2 variables. So it's a 2x2 grid of care map. So we are only doing pairs of adjacent one. And if the ones appeared in two different loops, that is fine. You can make use of it if that helps you to minimize the functions. The aim is to include each one is at least one loop by using the minimum number of loops. So we want to loop all the ones if possible, and then we want to have the minimum number of loops. So to illustrate the steps that mentioned just now, step 1 to step 4. So we use our very first example. So we have this Boolean expressions, and we have put that onto our care maps. So this is x bar y. So x bar y, we got a 1 there. And then we have x, y bar, we got 1 there. And then x, y, we got a 1 there. So the first step is to identify all the pairs of 1 and on the map horizontally and vertically. So horizontally, here we got a pair of 1. And then vertically here we got a pair of 1. So here is diagonally, so this is not adjacent. So this is not cannot be used as a simplification. Okay, so we want to draw loops. So we draw loops horizontally of a pair 1. And then we draw another loop vertically. Okay, so we have 2 loops. And here we have a 1 that included in 2 of the loops, so it's okay. So 1 can be used or can appear in 2 different loops, as mentioned in step 3. And the aim is to include each one in at least one of the loops. Okay, so we have all the ones being included in all the loops. And we can only draw minimum number, or we want to draw the minimum number of loops. So in this case here is 2 is the minimum. We cannot draw any smaller number of loops to include all the 1 in this case. So 2 loops. Okay, so that's what we have drawn just now. So we have here label it at loop A, which is the vertical loop, and then the horizontal I call it loop B in this care map. So how do we minimize the functions? So in this case here, if we look at loop A, so this is my loop A. So all the variables involved in my loop A, we have y, and then we have x bar x. So in this loop here, you can see that the variable x changes from x bar to x. Okay, so x bar changes to x in this loop. So if you look at the vertical loop, our loop A, just go from x bar to x, while y doesn't change. So y remained the same, but x changes from x bar to x. So in this case, the variable that changes state, we can eliminate them. So in this loop here, we can set that the loop has a value of y. So loop A has a value of y because x changes from x bar to x. So this value of y is known as the prime implicant. Similarly, for loop B, you can see that in loop B, y variable changes from y bar to y. Okay, so it's going from left to right. It's going from y bar to y, while the variable x hasn't changed, so it remains as x. So the prime implicant here is x for the loop B. And then what we do is we OR together all the prime implicants. So in this case here, we have two loops. So we have two primes implicant. One is y from loop A, and then from loop B is x. So our functions is x or y. So we started off with this functions here, which has three minterms, and the same functions is now simplified or minimize to x or y. Means that if I have a Boolean expressions of x or y, it's do the same thing as this Boolean expressions here on the top. So if you to build a logic circuit, you can appreciate that here use a lot of logic gates to implement these functions, whereas this function here, the function at the bottom, is just an OR gate. So this is a minimize functions, and this is a full functions, and this is what we call a standard form functions. And this is a minimize function. And we have done the minimizations using KMap. Okay, so here is another example. You can try this and see whether you can work out the minimize functions of this using the KMap and using the steps that discussed just now. Okay, so first, we want to translate the functions into KMap. So we have a minterms here, x bar and y bar. So x bar, y bar. So we put a 1 here. The second minterm is x bar y. So x bar y. So we got a 1 here. And then we got x and y. So x and y. Got a 1 here. So meaning that this terms here is missing. So the next step, so step 1, is to identify all pairs of adjacent one on the map. So horizontally, So here we have a pair of x. Oh, sorry, a pair of y. Vertically, here we got another pair of 1. So on my blue one, so we draw loops around it. So on my loop 1, so this is my loop 1. Okay, you can see that x bar in this loop here, x bar hasn't changed, whereas the variable y going across the loop go from y bar to y. Okay, so the variable y has changed state from y bar to y, so we can eliminate it. So this prime implicance for this loop 1 is x. And then for loop 2, okay, so loop 2 going vertically. So the variable x changes from x bar to x, whereas the variable y hasn't changed. So this is my loop 2. So going vertically in my red loop, loop 2. So y hasn't changed, remain as y, whereas x changed from x bar to x within that loop. So meaning that we can remove x, the variable x, and therefore loop 2 prime implicant is simply equals to y. And then the final functions is the OR the 2 prime implicants. So we have one implicant x bar and the other one is y. So we OR the 2 together, means that this function can be minimized to x bar OR with y. So another word, if we were to build a logic circuit of this, it's the same as if we build a logic circuit this. You get the same output from these 2 logic circuits. Here's another one. So to put it onto KMap, so translate the functions into KMap. So we have x bar, y bar. So here is x bar. And then y bar on the top. So we can put a 1 here. Then we have x, y bar. So this is x. Okay, x here. And then y bar. So this will be a 1 here. And then we have x and with y. So x and with y. That will be a 1 here. Okay, so I put some color there. Hopefully that helps you to understand how from the minterms is put onto the care map. So the next step is to identify all pairs of adjacent one on the map and then draw loops around each pair. So vertically, so here we have a pair of one, so we can draw one loop, and then horizontally we have another pair of one, and draw another loop here. Okay, so loop one. So this is my loop one. So I can see that in this loop, so going vertically, y bar is the one that remained the same throughout this loop one, whereas the variable x changed from x bar to x. Therefore, we can eliminate the variable x, and the prime implicance of loop one is simply equals to y bar. And then loop two, the variable y change from y bar to y, and then x stay the same. So the prime implicance of this loop is x, and therefore this functions minimize to x or y bar. So it means that this function is also equals to x or with y bar. Okay, so that is the solution to this example. And that is for two variables, care maps. So going to three variables, so if we increase the number of variables is our Boolean expressions, then the number of terms increase. So remember I said the variable is n, and then this is 2 to the n, and then this is 2 to the 3. So it means that we have n terms or n possible min terms in our expressions. To draw out the care map, so we can put one variable on one axis and then two variables on the other axis. And if you look at how the variables are listed on the care map, is very important. This doesn't follow your normal binary, but instead it uses gray code. So it means that you can only change one variable at a time. Okay, so here go from 0, 0, and then here is 0, 1, and here is 1, 1, and here is 1, 0 for the variable y, x. For the variable x, let's go from 0, 1. Okay, so if you look from left to right, the variable from 0, 0 to 0, 1, so only z changes from 0 to 1, and then from 0, 1 to 1, 1, so z stay the same, y change from 0 to 1, or y bar to y, and then from 1, 1 to 1, 0. Z is the one that changed, Y stayed the same. So Z changed from 1 to 0. And in actual fact, this K-map is actually wrapped around. So meaning that my 1, 0, if I go around back to the beginning, it also changes 1 bit or at a time. So from the 1, 0 going back to the beginning become 0, 0, which is also 1 bit change. So here I list down the index here related to the normal binary number. So it's coming from, so if I list my variable as x, y, and z, and x is the most significant bit, and z is the least significant bit, you can write down the binary number of x, y, and z. And let's go from 0, 1, and then skip to 2, and then go back to 3. Okay, so you go from 0, 1, and then 3, and then 2. And then repeat, not repeat, carry on from the second row. Let's go 4, 5, and then 6, skip 1, and then come back 7. Okay, so this is the 3-variable K-map. So for the cell A, the mean term is x bar, which is this x bar, and yz, and that's the mean terms for x. And for the cell B, we have x, and then y bar, z bar. Okay, so that is the relationship between the mean term and the location on the K-map. So how we can minimize 3-variable expressions. So here I have expressions here. So we have x bar, y bar, z bar. So this is x bar, y bar, z bar. So we put a 1 here. And then here we have x bar, and z bar, and z. And then we put a 1 here. And the last mean term again is x bar. Then with x and y. So put a 1 here. The rest of the mean terms is absent from this expression, so we put 0 for the remaining of all the location on the K-map. And then we can draw loops, identify a pair of ones adjacent to each other. So loop A, so this is my loop A, which is the red one. So you can see here, x bar stay the same, going from left to right. If I look at these two variables, this is where the loop is. You can see that y bar hasn't changed, but z changed or z bar change to z. And therefore we can eliminate z in this loop. So therefore this prime implicance of loop A will be equals to x bar, y bar. So we eliminated the variable z in this loop. And then loop B, here we can see that again, x bar hasn't changed, whereas in this loop here, so we're looking at this loop here. So in this case here, z hasn't changed. So z in this loop, z stay the same, whereas y going from y bar to y. So we can drop y, we can eliminate y from this loop. So the prime implicant of loop B will be equals to x bar z. And then the final step, so we all these two prime implicants, and that will be equals to this function here. And we can factorize this by taking the common factor of x bar, and this will be equals to x bar or with y bar, sorry, x bar and with y bar or z. So meaning that this function here can be minimized to this. So in two variables, we start off with identifying a pair of one adjacent to each other. So in three variables, we know that there is 8 possibility in the K-map, or 8 possible minterms. And the loop that we can draw is not restricted to just a pair of one, but instead we can group 4 ones that adjacent to each other. So in general, the loops in K-map is 2 to the end, depending on how big is the K-map. So here is 2 by 4. So the maximum is 8. So I can draw 8 ones in a K-map. I can draw a loop over all 8 of them. And if you do that, you see that all variable changes within that big loop. That means that you can eliminate all the variables, which means that cover all possibility. This means the function is equals to 1. It's always true. But here we have 6 ones here, so we can group them in a group of 4. Okay, so we have loop A here, and then loop B here, which is a group of 4 variables. Okay, so let's look at one loop at a time. Loop A. Okay, so my loop A here. Okay, you can see that within that loop, X changes from X bar to X, and this Y bar stay the same, and then X bar change to, sorry, Z bar change to Z. And therefore we can eliminate X, we can eliminate Y. Therefore, only Y bar that is remain constant in this loop. So the prime implicants of loop A is equals to Y bar. Okay, the next loop. So here you see that within my blue loop, X also changes from X bar to X. And here, Y is the one, or Z is the one that remain the same. Y change from Y bar to Y. So we can eliminate Y, eliminate X. So the prime implicants here is simply equals to Z. So the final functions of this after minimizations will be equals to Y bar plus Z. I can see that X doesn't come into play in these functions after minimizations. So here is another example. Okay, so I will do this. You don't have to, but you can try it. So the first thing is to draw out the truth table and then minimize the expression using Kmap and then draw a circuit. Okay, I got a question. Let me have a look. Okay, yeah. So the knots that I put down there is incorrect. So is first one is X bar and Z bar. Sorry, it's correct. It's X and Y that changes in this one. So X changes, Y, no, Z changes, but the second one is the one that is incorrect. So Y changes, this one, and then Z stay the same in the loop. Okay, so thanks for the comments, and thanks for the corrections. Okay, so this I'll take this as an example rather than exercise. So we're going to draw a truth table. So you're given the functions of this in 3 variables. First, you want to draw the truth table and then minimize the function using Kmap and then draw a circuit to implement that functions. So how do you put this into a truth table? So this is X bar, Y bar, Z bar. So this simply equals to 0, 0, 0. This is 0, 0, 1. This is 1, 0, 1. This is 1, 1, 0. This is 1, 1, 1. So first one, 0, 0, 0, which is this. So we put a 1 here. And then 0, 0, 1. 0, 0, 1, we put a 1. And then 1, 0, 1, put a 1. Then 1, 1, 0, put a 1. Then 1, 1, 1, put a 1. So that's how we can fill up our truth table. The other thing I want to point out, when you draw a truth table, it's very important that you list them in the order of the number. So for example, 0, 0, 0 is a decimal equivalent of 0. 0, 0, 1 is 1. So you want to list from 0 to 7. Don't list it in any order you like, because if you're not correct in the truth table to do that, because you end up with the functions of the minterms is not in the right order. Okay, so from there, so from the truth table, you can fill up your Karnaugh. Okay, so I put a decimal equivalence of our X, Y, and Z. So this is the least significant bit. This is the most significant bit. And then I have my index location on my Karnaugh. So I got 0, which is referred to this 0 here. I got a 1. So I put a 1 on the Karnaugh. So I got 1 here, I got a 1, put a 1 there. And then 5, 6, 7, there's a 1, so 5, 6, 5, 6, 7, I put a 1 there. So again, I stress the importance of how these variables are listed. It's going from Y bar, Z bar, Y bar, Z, YZ, and then YZ bar. So again, you have to ensure one bit change at a time. And if you list it this way, so you go X, Y, and Z. So this form the nice correlations to your X, Y, and Z on the truth table, starting from 0. I mean, you could list it in this way. Still maintaining one bit change at a time. It still works on a Karnaugh, but it will just confuses anyone who read it, because it's not in the normal way of presenting. But it works equally fine, but you have to identify each cell by the actual variable that you list there. But if you list it in this fashion, which is more standard, then it will be easier to read for someone else. So the next thing is to identify all the adjacent pair of 1 or 4 ones if there is a possibility in this K-map. So in this one, we cannot draw 4 ones, so we can only draw a pair of ones. So here I have drawn one pair here, the blue one, and then there's a red one here, and then a black one here, and a slightly grayish one here. Okay, so remember the steps that we talked about earlier. We want to loop all the one, but we want to also have the minimum number of loop. So this loop here, this is we call it the essential prime implicant. So this loop has to be there. Okay, so it's essential. Here is also essential. But if you look at the red and the black loop, you can have either the red one or the black one. We have all the ones being looped. So if we loop both red and black, then we have one additional loop that is not necessary in this case if we're looking for the minimum functions. Okay, so which means that one of this loop is a non-essential. It's not non-essential prime implicant. So if I keep the red one, I can remove the black one. Or if I keep the black one, I can remove the red loop. The prime implicants of all the loop, I have listed them all here. So the blue one will have x bar y, means that y and x, or x bar and y bar, remain the same in this loop. Y changes, and then same as the red ones, we have x that changes, and then the black one we have the y that changes, and then the grayish one we have z that changes. Okay, so listing all the prime implicants here, and then we all them together in the functions. So to get the minimum Boolean expressions, so if I classify this black loop as non-essential, we can drop this in our final functions because this is redundant. So if I remove that black loop, all the ones would have been a loop anyway. Okay, so it means that the black loop is classified as non-essential prime implicant. Or alternatively, we can drop the red one. And this still perform the same function. So we're going to use this one. Okay, and we get the minimum. Yes.
Can you repeat the non-essential?
Okay, so the non-essential. So if, let me do this. Okay. So now I have deleted the black loop. So you can see that without the black loop, all my ones or in a loop. So meaning that the black loop is not necessary. So we call that a non-essential. So having that black loop or not having it, we have all our ones being in the loop. So if I draw the black loop, and that is just going to give us an extra prime implicant, meaning that it makes the functions a bit more complicated, but doesn't do anything additional because all the ones already in the loop. So in other words, we can drop this loop and still have the function doing exactly what we want it to do. Okay, so that makes that loop is non-essential. So in our functions, the final function, we want to all the prime implicants. So because the black one is non-essential, so we don't have to put that into our final functions. Okay, so we can remove that. So meaning that up to here is already sufficient to represent the functions what we want it to do. Okay, so does that answer your questions? Do you need further clarifications about the non-essential prime implicants?
So if I put back the black circle but remove the red loop, is that possible?
Yes, you can do that. Yes, you can do that. That will be this function at the bottom.
Okay.
Okay, so the function at the bottom is the one that you remove the red one, but you make the black one as an essential one. So the red one will become non-essential. Okay, so alternative will be the function at the bottom. So alternative will be the functions at the bottom, which making the red as a non-essential, and then making the black one as an essential prime implicant. Okay.
Okay, sir. Thank you.
Welcome. So to implement these functions, so we can use logic circuits, so a logic gate to implement them. So a bar, that is a NOT gate. So X through a NOT gate, that will be our Y bar. Y through a NOT gate. So X through a NOT gate is X bar. Y through a NOT gate will be Y bar. And the first prime implicant is AND X bar with Y bar. And then the next one is AND Y bar with Z. This is our output. And then the final one is X and Y. And then put all through an OR gate. So here I have a 3 inputs OR gate. If you don't have 2 inputs, you could do this. This, do the same thing. So just now I was mentioning about if we don't have a 3 inputs OR gate, we can implement it using 2 inputs OR gate, using the circuits that I drew here, using two input OR gate to implement the same functions. So moving on. Here is another example of 3 variables. I'm not going to go into too much details of this, but just want to point out that another way of defining a functions, one way is to use a truth table. So previous example, you're given the expressions. Here you're given a truth table. And then if you list the variable in the order that I mentioned just now, from 0 to 7, which is the highest or the most significant bits. Sorry, no, the higher order of the variable of the binary number. Then the functions listing from 0, 0, 0 all the way to 1, 1, 1. And these functions, if we list it down as a binary number with the bits here as the most significant bits and here as the least significant bits, we call this the characteristic number. So you can list it as a binary or as a hexa number. Okay, so here in terms of hexa, we divide it into 4 bits and convert it 4 bits at a time. So this is 8 and this is 10. 10 is A in hexa. So we can list this as a characteristic number of the functions. So here I put a note here. Instead of giving the truth table, we can give a function or define a functions defined by the characteristic number. So an example, instead of giving the truth table, can give the information as a 3 variable function has a characteristic number A8H or in hexadecimal. That means that these functions have this truth table. Okay, so there's an alternate way of dishing out information, either with the Boolean functions or with a truth table or with characteristic number of the functions. 3 different ways of giving the same information. So you need to familiarize yourself with all 3 different ways of giving out the same information. So from here, we want to put it into CAMAP and then minimize it. So in this case here, that's how you go from truth table to CAMAP. I hope you're well understood now how you can put that into CAMAP. And then you want to loop it, identify groups of 1, and then loop it, and then finds the prime implicants of the loop, and then derive the minimize functions from the CAMAP. And then implement this circuit using your normal gate or basic gate that we learned about earlier. So what I'm going to illustrate from this example is to look at other implementations. So instead of using the basic gate, your AND and OR gate, we can also implement this using our universal gate, such as a NAND gate or a NOR gate. And to do that, we took our minimize functions and then perform a double inverse of that functions, and then apply our De Morgan's theorem. So now here we have a NAND gate. Here is another NAND gate, and then these two is named together as well. So there's 3 NAND gate here to implement that function. That's indicated here. So one of this is an NAND gate, and then another NAND gate, and then overall another NAND gate. So for the same minimize functions earlier on that that being implemented using AND gate and OR gate, I'm sure from the laboratory you know that to do this requires 2 different chips. And here you can implement that same functions using a single chip, like the one that you use in the lab, such as 7400. And to prove that they are the same, so we start off with the truth table that they're given, and we now can derive the truth table for these minimize functions using NAND gate. So here we take these 2 columns, X and Y, and then if we AND them, we can list down all the AND outputs of that. So meaning that something not right. Sorry, I'm looking at the wrong columns. So this is X and Z. So only both columns that has a 1, that will give me a 1. So this gives me a 1. This gives me a 1. And then we inverse this. Okay, so when 0 become 1, and then next we look at Y and Z. Again, it's an AND functions. So only when both the column has a 1, will give us a 1. And the rest will be 0. And then we take the inverse of that. And then we AND this or NAND this. Okay, so when both is equals to 1, we get a 1. Inverse of that will be 0. If both is 0, that will give you a 1. Okay, so in other words, only when we go through our NAND gate. So 0, 1. Sorry, here is looking at these 2 columns. Okay, so 1, 1, N give you a 1. This should have a bar. Okay, I know what's wrong. Okay, so this should be an N of these 2. of these two columns. So when both columns is 1, give us a 1. And then the final output function is the inverse of these columns here. Then we're showing that these two columns are identical. Okay, so that proves that this circuit is doing exactly the same as what is given in the original truth table. This is another example. So this is now moving into 4 variables. Okay, so we have A, B, C, and D as the inputs. And then the output is F, which is the Boolean function. And this is given in a truth table. And I also list down the characteristic number of these functions in hexadecimal, which is CC08. And for 4 variables, the K-map, we list that in the vertical axis as A, B, and then the horizontal axis as CD. And then again, if you look at the axis, there's a gray code 00011110. Or another word, this is A bar, B bar. This is A bar, B. This is A, B. This is A, B bar. This is C, B bar. D, and C, D bar. Okay, so this is another way of writing it, but it's easier to write 00011110. So in the following slides, I will use 0001 as the axis instead of writing down the variables as A and B. And then the corresponding cell related to the binary number of the inputs A, B, C, D, I have listed down them in red. So going down from 0 to 15 of my decimal equivalents of our binary number of A, B, C, and D, I can identify the locations of the K-map. So let's go from 0, 1, and then skip 2, come back to 3, then 4, 5, skip 6, come back to 7, and then skip the row, go from 8, 9, skip 10, come back to 11, and then go back to the third row, 12, 13, 14, and then 15. So you can go from here into the right location on the K-map. So in this case here, I got a 1 at 3, and 3 is here. I can put a 1 there, and then I go 1 at 10. So put a 1 there. The 11, got a 1 there. And I got 14, 15, got a 1 there. Okay, that's how you map from the truth table to the K-map of a 4x4 K-map for 4 variables. So in this module, we only go as far as 4 variable, because if we go up to a 5 variable, the K-map will be 3-dimensional. And that will be very difficult to do on paper. Okay, so we're going to do as far as 4 variables for this module. So we have our care maps draw up, and now we need to identify loops. And here we identify a loop of 4 and a loop of 2. And in a 4x4 care map, we can have a loop of 8 as well. So if I go in this fashion, if I have 1 there, I can loop a loop of 8. If I loop a loop of 16, that will be everything on the care map, and that will be equals to 1. And in this case, if we minimize these functions, this loop of 4, you can see that my A stay the same, my B changes from B to B prime, and then my C stay the same, and then my D changes. So we have A and C in the red loop, and then the blue one. So in this case here is an example of that our care map is wrapped around. Okay, so my 1 here is actually adjacent to this one on the other side, because our care map, the edge of this side is wrapped around to the other side. Same thing on my right is wrapped to the left, and then the top is wrapped to the bottom. So this one is adjacent to this one, so we can draw a loop there. So in this case here, the blue one, so will be this and this. So in this case here, you can see that our B bar stay the same, and then our A changes. And then this C and D doesn't change. So we have B bar, C, D. And then put that into a circuit, implement it into a circuit. We have B through a NOT gate, and then we have AND gates to end all this variable, and then all together to end up with a final functions. Okay, so that is 4 variables. And when we design digital electronic circuits, sometimes we have situations where the output, we don't really care whether it is true or false, or high or low. So in such scenario, we call it a don't care condition. So which means that we doesn't really care whether the output is 1 or 0. Or in other words, that particular combination of inputs is not a valid input for the system. So we don't use that input. So in that case here, with that input, we don't care what the output is. So in our functions, or in our truth table, we put an X there to represent a don't care scenario. And we use the X to our convenience. So meaning that if the X is high, will help us to minimize our functions, we'll use X as high. If not, we'll use it as 0. Okay, so in our previous example, the x there was 0, but now that one, if that particular combination of input is a don't care, so we put an x there. So we can make use of that x to simplify our, or to minimize our functions. Okay, so this was the original loop. So with the x there, we can make that x to 1. And now we can use a group of 4 of 1 to further minimize our functions. So in this case here, this loop here, we can see that A and B both changes, but C and D doesn't change in this loop. So this prime implicance has changed from previous one, which is B bar CD, into CD. So we eliminated B by using the don't care condition as 1. And then this is the implementation of this circuit. Okay, so we're going to use the don't care conditions to our advantage. Just to illustrate the point, if we have a don't care scenario here, so we can see that if we make this into 1, that's going to complicate our functions. So we'll keep that x to be 0 because we can't draw any loop to link to our existing 1 to further minimize the function. So in this case here, this x doesn't play into our advantage. So we'll keep this x as 1, not as 0. And then this x will be 1, for example. Okay, so that is to illustrate a don't care condition. Inversing a logic. So if this is our truth table, I'll minimize function p from these two loop with these 2 prime implicants can be written as this. So if you want to work out the inverse of p, then on our truth table, it will be those 0 become 1 and 1 becomes 0. And then we can draw our loop again, and we can simplify our p bar, and that will be equals to this minimize functions. Okay, so this is just to illustrate on KMap, if we were to inverse the functions, we're just going to make the 1 to 0 and 0 to 1 on the KMap. And then we can make our minimization the same way as before by drawing loops around group of 1. Okay, terminology. So I talked about minterms previously. So the minterms is actually the products. So in this case here, we have A, B two variable functions. So if I list down all our possibility of A, B, so 0, 0, that implies that is A bar, and with B bar, and the minterms will be A bar and with B bar for 0, 0. And we call it M naught, or with a small m. We haven't talked about the alternative. So far we talked about sum of products, and that's leads to our minterm, the sum of the minterms. But there's another representation of Boolean expression is called product of sum, and that's linked to maxterm. And for A and B both 0, the maxterm is A plus B, and we call that with a capital M sub 0. And the equivalence of the minterms and maxterms is that the minterms is equals to the inverse of the maxterm. Okay, here is just list down all the minterms for two variables, and here's the maxterm of the two variables, and this is the equivalent. And then for three variable, you can extend this, so they should have 8 different combinations. And then we have M0 to M7. I did not list all of them out. I'm sure you can work that out yourself. Okay, so the M0 is A bar, B bar, C bar, all the way to M7 is A, B, and C. And then the maxterm is A plus B plus C, and then M7 is A bar, or with B bar, or with C bar. Again, the equivalence of the mean and the maxterm. Here's the proof of their equivalence. So in two variables, if I take my M0, there will be A bar and with B bar. And if I inverse that, and then apply our De Morgan's, so applying De Morgan's, this will be A bar bar plus B bar bar. So we break this bar and change the sign. And therefore we have A bar bar, that will be A, or with B bar bar, and that will be B. And then A and B is our maxterm. Therefore, our minterm is equals to our inverse of the maxterm, or the inverse of the minterms is equals to the maxterm. And here is the proof of the three variables, and you can extend that to 4 variables as well. Okay, you can show that they are equivalent.